Introduction. Welcome to Gate and Kernel, where we look beneath the software and explore how computers actually work, from logic gates to processors, memory, operating systems, and modern computing hardware. Computers can process text, images, video, programs, websites, games, and artificial intelligence. But underneath all of this complexity is a surprisingly simple idea: binary. Binary uses only two digits, 0 and 1. Processor registers contain bits. Memory stores bits. CPU instructions are encoded using bits. Files and network data are ultimately stored and transmitted as patterns of bits. Before learning how CPUs, memory, and digital circuits work, we need to understand binary. Chapter 1. What is a binary number? Most people use the decimal number system. Decimal is base 10 because it uses 10 digits, from 0 through 9. Binary uses only 0 and 1, so it is called base 2. A binary number may look like 1101. Like decimal, binary is positional. Each digit has a value based on where it appears. Decimal positions use powers of 10. Binary positions use powers of 2. Chapter 2. Why do computers use binary? The main reason comes from electronic hardware. Digital circuits can reliably distinguish between two logical states. We can think of them as low voltage and high voltage, or conceptually as off and on. Low can represent 0. High can represent 1. Real electronics are more complicated, but this two-state model is extremely useful. From these two states, engineers can build logic gates, adders, registers, memory cells, CPUs, and complete computers. Binary is closely connected to how digital hardware is physically built. Chapter 3. What is a bit? The smallest basic unit of digital information is the bit. The word bit comes from binary digit. A bit can contain only 0 or 1. So one bit has exactly two possible states. 0 might mean off and 1 might mean on. Or 0 might mean false and 1 might mean true. The meaning depends on the system, but the bit itself still has only two possible values. Chapter 4. More bits create more possible patterns. One bit gives two possible patterns. 2 bits give 4. 3 bits give 8. Every additional bit doubles the number of possible patterns. The rule is simple: n bits can create 2 to the power of n patterns. 5 bits give 32 patterns. 8 bits give 256. 16 bits give 65,536. 32 bits give more than 4 billion. This relationship appears everywhere in computing. Chapter 5. Understanding decimal place values. First, consider the decimal number 527. The 7 is in the 1's position. The 2 is in the 10's position. The 5 is in the 100's position. So the number means 5 times 100, plus 2 times 10, plus 7 times 1. Moving one position to the left multiplies the place value by 10. That is why decimal is called base 10. Chapter 6. Binary place values. Binary works the same general way, but its place values are powers of 2. Starting from the right, they are 1, 2, 4, 8, 16, 32, 64, 128, and so on. Each position is twice the value of the position to its right. The rightmost position is 2 to the power of 0, which equals 1. This doubling pattern is the key to reading binary numbers. Chapter 7. How to read a binary number. Consider binary 1101. Its place values are 8, 4, 2, and 1. A 1 means the place value is included. A 0 means it is not. So 1101 means 8 plus 4 plus 0 plus 1. That equals 13. Therefore, binary 1101 represents decimal 13. Once you know the place values, binary becomes simple addition. Chapter 8. Another binary to decimal example. Now consider binary 10110. Its place values are 16, 8, 4, 2, and 1. The 1 bit selects 16, 4, and 2. Add them together. 16 plus 4 plus 2 equals 22. So binary 10110 represents decimal 22. The method is always the same: add the place values where the bit is 1. Chapter 9. Powers of 2 you should recognize you do not need to memorize huge binary numbers. But common powers of 2 are worth recognizing. They begin with 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1024. You will see these values repeatedly in computer architecture because they appear naturally in binary systems. Chapter 10. Converting decimal to binary. Suppose we want to convert decimal 13 into binary. Use the place values 8, 4, 2, and 1. 13 contains 8, so the first bit is 1. 5 remains. 5 contains 4, so the next bit is 1. 1 remains. 1 does not contain 2, so the next bit is 0. 1 contains 1, so the last bit is 1. The result is 1101. Chapter 11. Decimal to binary using repeated division. There is another common method. Repeatedly divide the number by 2 and record the remainder. For 13, the remainders are 1, 0, 1, and 1. Read them from bottom to top. The result is again 1101. Both methods work. For computer architecture, however, becoming comfortable with powers of 2 is especially useful. Chapter 12. What is a byte? Computers commonly organize bits into groups. A group of 8 bits is called a byte. 1 byte equals 8 bits. For example, 01000001 is 1 byte. 8 bits can create 256 different patterns. If those patterns are interpreted as unsigned integers, they represent values from 0 through 255. Chapter 13. Why 8 bits give 256 values but only go to 255? 8 bits provide 256 possible patterns. So why is the largest unsigned value 255? Because 0 is one of the values. The range from 0 through 255 contains exactly 256 numbers. In general, the maximum unsigned value represented by n bits is 2 to the power of n minus 1. Chapter 14. Unsigned binary integers. An unsigned integer represents only 0 and positive values. With 4 bits, the range is 0 through 15. With 8 bits, it is 0 through 255. With 16 bits, it is 0 through 65,535. With 32 bits, the maximum is 4,294,967,295. The rule is always 0 through 2 to the power of n minus 1. Chapter 15. Bits and larger data sizes. Computers commonly use standard bit widths. 8 bits equal 1 byte. 16 bits equal 2 bytes. 32 bits equal 4 bytes. 64 bits equal 8 bytes. A 32-bit value contains exactly 32 binary digits. As the number of bits increases, the number of possible patterns grows extremely quickly. 32 bits provide 2 to the power of 32 patterns. 64 bits provide 2 to the power of 64. Chapter 16. Binary addition. Computers do not only store binary values. They also perform arithmetic. Binary addition has 4 basic cases. 0 plus 0 equals 0. 0 plus 1 equals 1. 1 plus 0 equals 1. And 1 plus 1 equals 1. 0 in binary. That last rule is important. Binary has no digit 2, so we write 0 in the current position and carry 1 into the next position. Chapter 17. A simple binary addition example. Consider binary 0101 plus 0011. The first number is 5. The second is 3. So the result should be 8. Adding them in binary gives 1000. And binary 1000 represents decimal 8. The arithmetic is the same. Only the number system is different. Chapter 18. Binary addition with carry. Now consider binary 0111 plus 0001. That is 7 plus 1. Starting from the right, 1 plus 1 gives 0 with a carry of 1. The carry continues through the next positions. The final result is 1000, which is decimal 8. This carrying process is important because processor arithmetic circuits use the same basic principle. Chapter 19.
Why binary addition matters inside a processor. Circuits called adders combine binary inputs and produce binary outputs. At a low level, an adder determines two things: the result bit and whether a carry must pass to the next position. Logic gates can perform these operations. Larger groups of these circuits can add 8-bit, 32-bit, or 64-bit values. Binary arithmetic therefore connects number representation directly to digital hardware. Chapter 20. The least significant and most significant bits. The rightmost bit is called the least significant bit, or LSB. The leftmost bit is called the most significant bit, or MSB. In an unsigned 8-bit value, the LSB represents 1. The MSB represents 128. That is why changing a bit near the left side usually changes the numerical value much more than changing a bit near the right side. Chapter 21. Binary is about patterns. Binary is not only about numbers. A group of bits creates a pattern. For example, 01000001 is one 8-bit pattern. There are 256 possible 8-bit patterns. The same pattern might represent a number, a character, part of a CPU instruction, or something else. The bits do not change. The interpretation changes. That idea is fundamental to computer architecture. Chapter 22. A quick review. Binary uses 0 and 1. Each binary digit is a bit. 8 bits form 1 byte. Binary place values are powers of 2, 1, 2, 4, 8, 16, 32, 64, and so on. With n bits, there are 2 to the power of n possible patterns. The largest unsigned n-bit value is 2 to the power of n minus 1. Binary addition also uses carrying, just like decimal addition. Conclusion: binary numbers are one of the foundations of computing. Processor registers contain bits. Memory stores bits. CPU instructions are encoded as bits. Files, images, audio, programs, and network data are ultimately represented as patterns of bits. In Part 2, Binary Inside a Computer, we will move beyond basic numbers and see how these patterns can represent negative numbers, characters, memory values, CPU registers, machine instructions, addresses, images, and other digital data. The key idea is simple. Computers do not just store numbers. They store patterns of bits. And the meaning comes from how those patterns are interpreted. This is Gate and Kernel. If you enjoy clear explanations of how computers work from the hardware up, subscribe and continue with the next part. From logic gates to kernels, we look inside computing. Thanks for watching.